Have you ever stopped to think that maybe, just maybe, reality has a rule book? A set of hidden instructions that tells everything what to do, from a simple falling apple to a massive soaring rocket. Well, it does. And today, we're going to take a little peek inside. So get this. What could a guitar, a bucket filling with water, and a giant floating ship possibly have in common? I know, it sounds like the beginning of a really bad joke, right? But the answer is actually, well, it's pretty profound.
Yep. They all play by the exact same set of rules, the rules of physics. And that's what we're doing today. We're going to pull back the curtain on some of these amazing rules that are happening all around you, all the time, hiding in plain sight.
Okay, first up, let's talk about motion. We see things move every single day, right? It's so common, we don't even think about it. But physics gives us this incredible language to describe not just that things move, but precisely how they move.
When we think about force, we usually just picture a straight push or a pull. But a force can be more clever than that. It can also create a twist, a turn, and that turning effect has a name. It's called the moment of force. It's the big difference between just shoving something forward and making it spin.
And this shows it perfectly. Think about it. If you push a bowling ball right in the dead center, it's just going to roll forward in a straight line. Simple. That's what we call translational motion. But if you take that same push and apply it to the edge of a wheel that's stuck on an axle, it's not going anywhere, is it? It's just going to spin. That's the moment of force in action, creating rotational motion.
All right, here's a classic physics brain teaser for you. You could be pushing something with all your might. You're getting tired, you're sweating, but according to the rule book of physics, you might not be doing any work at all. How on earth is that possible?
This is such a cool and fundamental idea. You could lean against a brick wall and push with everything you've got for an entire day. But in physics terms, you've done zero work. Zilch. Nada. Why? Because the rule is super clear. For work to be done, your force has to actually move something. It has to cause displacement. If nothing moves, no work is done. Period.
And work is basically how we move energy around. That energy usually shows up in one of two ways. You've got potential energy, which is just stored up energy. Think of a ball you're holding way up high. It's got the potential to do something. Then there's kinetic energy. That's the energy of motion itself. It's what happens the second you let go of that ball and it starts falling.
So let's put that to the test. Quick thought experiment. Imagine a huge horse and a little tiny dog, and they're both running at the exact same speed. Which one has more of that motion energy, that kinetic energy? It's the horse, and it's not even a competition. See, kinetic energy isn't just about speed, it's also about mass. So because the horse has so much more mass, it is packing way more kinetic energy. It would take a whole lot more work to bring that horse to a stop than it would to stop the dog.
Okay, so we've talked about the forces that move things. Now let's switch gears and talk about the actual stuff itself. What even is matter? What are its most basic properties?
So, how do you measure the volume of a lumpy, bumpy rock? You can't exactly use a ruler on it. Well, physics has this ridiculously clever and simple solution. You just see how much water it pushes out of the way. You drop it in a cylinder of water, and the amount the water level rises, that is the exact volume of the rock. It's so simple, but it's perfect. All right, here's another situation you see all the time. Let's say you take a pot of water and you heat it up, but not quite to boiling. What's actually changing? Is its mass changing? What about its volume or its density? Let's break it down.
First off, the mass. This one's an easy one. Its mass stays exactly the same. You haven't added any new water molecules, you haven't taken any away. The total amount of stuff in that pot is constant.
But this is where things get really interesting. The volume actually increases. When you add heat, you're just pumping in energy. The little water molecules absorb that energy and start zipping around like crazy, pushing each other further and further apart. It's called thermal expansion. The same amount of stuff starts to take up more space. So think about it. If you have the same mass, but it's now packed into a bigger volume, what does that do to the density? It has to go down. The liquid becomes less dense. And this one little fact, that hotter fluid is less dense than colder fluid, is the key to understanding so much about our world.
Including this is how things float. It all comes down to the law of flotation. Basically, an object will float if it can push aside an amount of fluid, and that could be water or even air, that weighs the same as the object itself. It's like a cosmic balancing act between the object's weight pushing down and the fluid pushing back up.
A hot air balloon is the perfect example. The whole thing, the balloon, the basket, the people, is way less dense than the ocean of air around it.
It's so light for its enormous size that the air it shoves out of the way actually weighs more than the balloon itself. So the air literally shoves it upward. It's floating, just in a sea of air instead of a sea of water.
And for our last section, let's dive into the invisible physics that's all around us, the energy that we hear as sound, and the power that literally makes our modern world go round.
We talk about high notes and low notes all the time, right? But what actually is pitch? Well, in physics, pitch is just how our brains interpret frequency. When sound waves vibrate really, really fast, a high frequency, we hear a high-pitched sound. And when they vibrate slowly, we hear a low-pitched sound. It's that direct. A guitar is basically a perfect little physics lab for this. If you pluck a thin, light string, it's able to vibrate super fast. That gives you a high pitch. But if you take a string and you loosen it, you lower the tension, it's going to vibrate much more slowly, and that creates a lower pitch. It's a physical relationship you can see and hear.
And I guarantee you've heard this 1,000 times. When you fill a bottle or a bucket with water, listen to the sound. It gets higher and higher in pitch, doesn't it? Well, now you know why. It's because the column of air inside the bucket is getting shorter and shorter, and a shorter column of air vibrates faster, just like a shorter guitar string, which means a higher frequency and a higher pitch.
And what's so cool here is we can actually see what those sounds look like. Take a look at wave C. See how the waves are all scrunched up together? That's a high frequency. To our ears, that's a shrill high note. Now compare that to wave A. The waves aren't very tall, are they? That's low amplitude, which our ears hear as a soft, quiet sound.
Finally, let's talk about the magic of power. The devices we use every day are all energy transformers. A light bulb doesn't create light. It takes electrical energy in and transforms it into light and heat energy out. A loudspeaker takes that same electricity and transforms it into sound energy. It's one of the biggest rules in the book. Energy is never created or destroyed, it just changes its clothes.
So let's wrap this up. What have we learned from peeking inside the rulebook? We've learned that force isn't just a push, it can be a twist. That floating isn't some kind of magic, it's just a simple balancing act. That sound isn't just random noise, it's vibrating energy that actually has shape. And that all the energy in the universe is just constantly being transformed, but never, ever lost.
So really, the big takeaway here is that these rules aren't just for some stuffy textbook. They are happening right now, all around you. The sound of my voice, the light from your screen, it's all physics. So the real question is, now that you know a few of the rules, what's the first thing you're going to notice?